Welcome to my open learning session where I'm going to catch up with deep learning. So in this video, we're going to tackle chapter 2, linear algebra. Let's take a look on how long it is. The whole chapter is about 40 pages. Okay, so let's start. I will take most of my short scribbles here on this PDF. So let's start. When formalizing intuitive concepts, a common approach is to construct a set of objects, symbols, and a set of rules to manipulate this object. This is known as algebra. Linear algebra is a study of vectors and certain rules to manipulate vectors. The vectors many of us know from school are called geometric vectors. Okay. Geometric vectors, which are usually denoted by a small arrow above the letter. Okay, something like that. In this book, we discuss more general concepts of vectors and use a bold letter to represent them. Okay, that's... I really hate that math has like no real notation. Like every book has to introduce and try to needs to explain what the symbols mean. Okay. In general, vectors are special objects that can be added together and multiplied by scalars to produce another object of the same kind. From an abstract mathematical viewpoint, any object that satisfies these two properties can be considered a vector. Okay, so I think I'm not sure how much I should write. Yeah, so I feel like it's always easier to have a line where I show you where I am. At the same time, I do not want to scribble a lot. There's no laser tool here. Okay, anyway, let's just go on. So what's important here is, I think, that we have this sentence. Any object that satisfies these two properties are considered a vector. So which can be added together and multiplied by scalars to produce another object of the same kind. Okay, this is really important. Anything which we can add together or multiply by a scalar, and a scalar is just a number, is considered a vector. Anything. Okay, it's really hard for me to think of anything else than an arrow. Okay, so let's start. Number 1. Geometric vectors. This example of a vector may be familiar from high school mathematics and physics. Geometric vectors, see figure 2.1, are directed segments which can be drawn to geometric vectors x and y. I'm not sure how to pronounce this one. X what? X arrow maybe? Okay, I will just call it X arrow. X arrow and Y arrow can be added such that X arrow plus Y arrow equals Z arrow. Yeah, that makes sense, because you have basically two numbers and you just need to add them for each dimension. So you have to add x, like x coordinate for both vectors, and then the y combinator, the y number as well. Furthermore, multiplication by a scalar, lambda x arrow, where lambda is part of the real number set, is also a geometric vector. In fact, it is the original vector scaled by lambda. Therefore, geometric vectors are instances of the vector concept introduced previously. Interpreting vectors as geometric vectors enables us to use our intuitions about direction and magnitude to reason about mathematical operations. Okay, so they're saying that this whole thing is just an interpretation. They are not real errors. It's just we make them in our head to errors, but it helps us for our intuition. Okay, so the second part are polynomials. Polynomials are also vectors. Two polynomials can what? Can be added together, which result in another polynomial. And they can be multiplied by a scalar lambda, and the result is a polynomial as well. Therefore, polynomials are rather unusual instances of vectors. Note that polynomials are very different from geometric vectors. While geometric vectors are concrete drawings, polynomials are abstract concepts. However, they are both vectors in a sense previously described. Okay, so what they have here, figure 2.1. Okay, I think this is, at least this is new to me. Or maybe I knew it before and I forgot it. Different types of vectors. Vectors can be surprising objects. Okay. We have 4 lines. Okay. I don't know. Okay, I just see 4 lines. Yeah, so I see 4 lines. I'm not sure if they are in any kind of relationship to each other. But we can assume something like, let's take red and blue, and we can add them together to get a new, basically a new line. So we have 2 points. Do we? Would you add each point? Would you say here's a point, and then you just shift them up? Like in this case, we have, I don't know, 3, and here we have something like minus 1.7. So this point would be bumped 3 points up, which makes it, I don't know, what is it? 1.3, I guess. So here. But you will not add each point of the same magnitude. So, for example, this point, here we have in blue, I don't know, say minus 1, which means that this point would shift down. But it makes sense that you can take this line and then you add the other line and then you have a new line. And also you can just take any line and multiply it by a scalar, like make it twice as big or so, something like that. Okay, so I accept that. Makes sense. It's just that the name vector is really strongly associated with an arrow. So polynomials are also vectors. Okay, number 3. Audio signals are vectors. Audio signals are represented as a series of numbers. We can add audio signals together and their sum is a new audio signal. We can scale an audio signal. We also obtain an audio signal. Okay. Oh, wait. If we scale an audio signal, we also obtain an audio signal. Yeah, it makes sense. But what's the difference between an audio signal and a polynomial? I don't know. Okay. Number 4. Elements of Rn. Tuples of n real numbers are vectors. Rn is more abstract than polynomial, and it is the concept we focus on in this book. For instance, A can be, I don't know, a tuple of 3 numbers, 1, 2, and 3. In an example of a triplet, okay, triplet of numbers, adding two vectors a, b component-wise result in another vector. Moreover, multiplying a by lambda results in a scaled vector lambda a. Yeah, makes sense. Considering vectors as elements of Rn has an additional benefit that it loosely corresponds to arrays of real numbers on a computer. Okay, so, okay, I don't know. Many programming languages support array operations, which allow for convenient implementation of algorithms that involve vector operations. I think this part is the important part. Considering vectors as elements of Rn has an additional benefit that it loosely corresponds to arrays of real numbers on a computer. But is this not just a vector? Well, yeah, it is a vector, but is it not just a geometric vector? I mean, what's the difference? They're doing the same thing, right? Maybe it's the whole point that they're all the same thing. I think these different vector types, if you want so, are just interpretations we have. So to know that if you see something like an array, that's a vector. If you see an arrow, it's a vector. If you see a polynomial, it's a vector. And an audio signal. I have a question here. Okay, I wrote this, yeah, I wrote this question down. Maybe they're not. Usually, if you see something like an audio signal, you think more like something like this. I loosely remember that these things are, they are sine waves, and like there's a way to construct basically any function with a bunch of sine waves. Maybe that's what they like. Maybe that's the difference. Not sure. Okay, let's go on. Linear algebra focuses on the similarities between these vector concepts. We can add them together and multiply them by scalars. We will largely focus on vectors in Rn, since most algorithms in linear algebra are formulated in Rn. We will see in chapter 8 that we often consider data to be represented as vectors in Rn. In this book, we will focus on finite dimensional vector spaces. Okay, that's helpful. In which case, there is a one-to-one correspondence between any kind of vectors and Rn. When it is convenient, we will use intuitions about geometric vectors and consider array-based algorithms. One major idea in mathematics is the idea of closure. This is the question: what is the set of all things that can result from my proposed operations? Okay, I didn't got the last one. One major idea in mathematics is the idea of closure. Okay, what is a closure? This is the question: what is a set of all things that can result from my proposed operations? Okay, so I guess something like you have a thing, and then you have a set of operations, and then you want to apply the operations on that thing. Now I guess the question is, what other things this will produce? Okay, this is, I think, important. Okay, in the case of the vector, what is a set of vectors that can result by starting from a small set of vectors and adding them to each other and scaling them? The result is a vector space. Yes. So you can have a bunch of things a bunch of vectors, and then you can add them and multiply them together to get basically an infinite set of new vectors, and then that whole possible set is called vector space. The concept of a vector space and its properties underlie much of machine learning. The concepts introduced in this chapter are summarized in figure 2.2. This chapter is mostly based on the lecture notes and books by Drum and Weil. Strange. Okay. Linear algebra plays an important role in machine learning and general mathematics. The concepts introduced in this chapter are further explained to include the idea of geometry in chapter 3. In chapter 5, we will discuss vector calculus, and which is where a principled knowledge of matrix operations are essential. In chapter 10, we will use projections for dimensionality reduction. Okay, so I think dimensionality reduction is quite important. It was one of those pillars. With principal component analysis. Okay, I think this PCA is a part of dimensionality reduction. In chapter 9, we will discuss linear regression, where linear algebra plays a central role for solving least square problems. Okay, and I think least square problems is some kind of optimization tool principle. Let's take a look at a graphic. A mind map of the concepts introduced in this chapter. All right, so we start with vector, and then we will understand that actually a vector is a property of linear independence. And then we will learn about the bases. These are basically the dimensions. And usually, yeah, it makes sense if you have something like dimensions that these are essential to know how to reduce dimensionality. On the left side, if we put a bunch of vectors together, then we can do something like a matrix and do calculations with that. The vector itself produces a vector space. I'm not sure what this is. Abelian with plus, question mark, linear affine mapping. And here on the left we have systems. Yes, it makes sense. Basically use a matrix to represent systems of linear equations, then solve them, and then you can reverse the matrix. We have to understand what that means. Some methods how you actually solve those linear equations, and then this all will lead to somehow classification and analytic geometry. Okay, nothing too crazy, I guess. All right, so now we are done with our introduction, and in the next video we will start with systems of linear equations.